Hi, we're Group 11, and our Project 2 presentation will be about PILS, which stands for Partially Parallel Imaging with Localized Sensitivity. So this is an overview of our project. So first we'll go into the background of PILS and what it is. Then we'll go into the theory and methodology on how we used to replicate PILS in our code. Next we'll go into results of our code, and then we'll finally discuss the findings of our code. So first we'll get into the background. So as we said before, PILS stands for Partially Parallel Imaging with localized sensitivity, and it is a type of parallel imaging which became prevalent in the year 2000. It is assumed that coils have localized sensitivity patterns. Each receiver coil has localized sensitivity over a specific region and zero everywhere else. And the main advantage of this type of parallel imaging is that it reduces time to produce the image. It does this by reducing the field of view region to a smaller region, which reduces the samples, which takes less time to create the image and is more effective in time. So next we'll get into the theory and the methods. So for the theory, like as we stated before, we assume that the coils have localized sensitivity patterns. So in the diagram on the right, Y sub C represents the region of each local coil sensitivity, which also stands for the field of view for each coil. Y represents the full field of view for the full image, and Y of I represents the reduced field of view due to the acceleration factor. And because of this acceleration factor, it can create sub-images, which we'll talk about later on how we can reduce and find the correct sub-images. And one of the main design requirements of PILs is that this Y sub I has to be greater than uh, the coil region, but less than the full field of view of the full image. So there are four main equations we want to talk about. Equation one below is the simple 1D Fourier transform where rho of y denotes the spin density. Then we can change the limits of this integral to denote the y sub c of a given coil centered at an offset value of y of 0, which gives equation 2. So this simplifies the integral so that it spans y sub c. So equation 3, we move on to equation 3 and 4, which shows that the summation is equivalent to the fast Fourier transfer of the received signal multiplied by a linear phase term, just so we can shift the reduced field of view, the center of the reduced field of view, and combine it with the correct reconstruction.
Okay. I'm Bryce. I'll be talking about methods and results we're using. So first, we're going to construct the simulation phantom. We use the MATLAB phantom function, and we create a 32 by 32 phantom so the encoding matrix won't be too big. This and second, we're going to create the encoding matrix, and this is adapted from the lecture from the homework. It's the same concept of doing the Fourier transform, and it can better control when we want an undersampled acquisition. We can just skip lines of the encoding matrix and get the undersampled case space. Then we're going to construct the coil sensitivities from the paper. We know that our profiles should be non-overlapping, and the sensitivity of each individual coil should be completely homogeneous. This means if we're looking at the y direction, there should be no variation in sensitivity in the x direction. Then we're going to simulate the undersampled acquisition. To do this, if we want an acceleration factor of 2, we just skip every other line in case space to achieve the reduction in acquisition time. Then we're going to encode the object using multi-channel coils. We multiply the encoding matrix with the coil profiles and then apply matrix to the object and then add noise. Last, we will construct the image using PILS. At this step, we will we'll reconstruct the image using only the signals from the predefined range of Y where the signal originated, and we'll repeat this process for every coil to get a unaliased full FOV images. Um, and then we'll combine those images to using Samuel-Square's reconstruction. And here's the results. Um, Here is the original object and it's fully sampled, it's at noise, and here we're using the code from the homework, and we're just showing like how you reconstruct the image using the conventional methods. And here we construct the coil profiles. Um, there are four coils, and each with a Gaussian distribution. And the YC is set to 8 because 4 times 8 equals 32, which covers the whole field of view. Um, and then looking at the results of of the oxidation rate at 2, we can see the upper right corner of the image is actually um the the reconstruction of the from the homework, and that's basically since reconstruction, and we're going to compare our PILS with that, and it's basically done by the code on the right. And for our methods, if we define y sub I to be the full field of view divided by r, which is acceleration factor, and the y naught is the center of the core sensitive region in the field of view, we can zero out other um, zero out the signals of other regions, and then we combine those using the sum of squares, and we get the reconstructed image at the lower corner, right corner of the image. And this is true for other acceleration factor. And here, just a gradients of R, and see how R will affect the intensity and the SNR in the reconstructed image. We can show that there's a decrease in image intensity and the cost in SNR as R goes higher. It's because reducing the number of phase code lines leads in itself to a reduction in SNR of square root R due to reduced Fourier averaging. And this is also discussed in the lecture as shown in this equation. And then we tested different coil localizations or profiles. Here we increased the width of the Gaussian profiles, which i.e. increased the YC. This covers more, individual coil covers more of the image. And we can see a better results because the strong signal coming from the center of one coil tends to diminish the impact of low intensity artifacts in the other uncoil images. But there could be a function to find where the sweet point is. As we increase the width of the YC more, we'll see artifacts because the YI is now less than YC, so we're combining a lot of aliases. And the key programming issues for that is we um, we first code the commented out section to get the integer number for skipping lines, and which makes the aliases move around the field of view because it's random moving the lines in a case space. But when we look at when we construct the under sampled encoding matrix from scratch, we'll get a better results because um, we change the delta ky, and let's get a better results for the aliasing. Okay.
Now we'll get into the discussion of our results and compare them to the original PILS paper. The first area where our paper or our code differed from the original paper was the coil sensitivity simulation. So in the paper, they used the Bio-Savart equation, and they made a MATLAB simulation for different coil geometries and computed the coil sensitivity as a function of distance. And it gave them this graph that they show below. Um, and in our code, we used a Gaussian, which broadly follows the same shape. Um, and one thing to note here is that the y-axis is logarithmic. So a Gaussian is a very fair assumption. Um, so while the paper used this coil geometry for the simulations of their phantom, when they moved to real human images, they used a Gaussian fit to find the centers of each of the coils in the image. So the paper listed a Gaussian as an appropriate fit, so we used that. One other area where our code differed from the original was we used an encoding matrix to compute the Fourier transform and the inverse Fourier transform. The way the paper implemented this was by cropping the signal that comes in from each of the coils and then using like a linear phase term to offset that in the Fourier domain. We get a numerically identical result. This is just easier to implement and less to debug. And the con to that is uh, it's less memory efficient. Um, Another comparison is on the image quality. In both our images and the paper's images, we see the signal sort of break down around 2.2 uh, based on the coil profile. So we also see that around there, the image gets more aliasing. Then the last area that I wanted to focus on was about the artifacts inherent to this PILS method. So as you can see on both the image that we created and the image from the paper, there are these stripe artifacts where there's like sort of wide hotspots in the image, and that's due to the hotspot of the coil being smaller than the area that the coil has to span. So this is like dependent on the coil design and how close it is to the patient and a lot of factors like that. So uh, we had those artifacts in both. Um, some of the limitations of the PILS method are that the it makes the assumption that the coil sensitivity is highly localized, meaning that it is zero outside the area that we mask out. So when it's not true, this method starts falling apart, even at lower acceleration factors compared to other methods like grappa. And we found some studies to show that in these less localized coils, other methods perform better. So our future work would include trying other methods that better deal with spread out coil sensitivity and more modern techniques of reconstruction. And here are our references, and thank you so much. That's everything for our presentation.